folks, in this video, we're talking about reaction enthalpy diagrams. What? Wait, what? Wait, what? Yeah. So we have a few objectives. I want you to be able to define enthalpy, at least loosely, because it's a funky term. And I want you to be able to characterize a reaction enthalpy diagram, at least a basic one. I want you to be able to define activation energy, which is kind of an important term. I want you to be able to then explain why it's an important term when we're studying reaction. So let's start by talking about enthalpy. Is the symbol H for enthalpy, and enthalpy is the total heat content of a system. Remember, heat is a kind of energy. We can think of it as thermal energy. And so a total heat content is equal to internal energy plus pressure times volume, which we can represent with this equation. Now, generally, if pressure is constant, that enthalpy is just going to really measure the heat flow through a system. So we can say H equals Q, or we're going to look at that a little differently. This is going to be true for most of the chemistry we do in a general chemistry sense. We're not controlling pressure, so pressure is going to stay pretty much constant at atmospheric pressure. So for most general chemistry, enthalpy equals heat flow. And we only really look at changes in enthalpy. We don't really measure the direct heat in a system. We look at the flow, the movement of heat. So reactions will either absorb heat into them, or they will release heat during the reaction. And so delta H is what we're really going to look at majority of the time when we talk about enthalpy. And that's the change in enthalpy, or how heat has flown or moved about during a reaction. So if we have a positive delta H, that means our reaction gains heat. It's endothermic. It absorbs heat. It's something that is going to make its surroundings feel cooler. And if we have a negative delta H, that's going to be an exothermic reaction. That's something that during the reaction, heat is lost. We have a loss of heat. So something like fire or combustion reaction releases heat as a product. We can think of it. Neat. And so the delta H only tells us the difference between enthalpy, or the enthalpy difference between our reactants and products. And this doesn't really tell us everything that's going on, as we will learn throughout this video. So we'll get to that. So let's talk about a reaction enthalpy diagram, which is sometimes called a reaction coordinate or reaction coordinates. That's a diagram that shows how enthalpy changes throughout a reaction. Whoa, that's pretty cool. So our y-axis, the up and down, that's going to measure enthalpy, or sometimes it's shown as energy for heat energy. And our x-axis, the left and right, that's going to show the progress of the reaction, sometimes called the reaction coordinate. And so our reactants are going to appear on the left side of it, and our products will appear on the right side. So kind of like how we read things. We start with our reactants, and on the other side are our products. Neato. So here are some examples. We can see an exothermic reaction. Here we lose enthalpy. We give it away. We have a negative delta H. So our reactants start at a higher enthalpy, and our products are down here. Or we have an endothermic reaction where delta H is positive. Our change in H is positive, so we go up in H, our y-axis. Neat. Oh, and here we have process of the reaction as our x-axis, or sometimes you will see reaction coordinate. Neat. So let's look at a simplified example. Here I've got our reaction. This is a combustion reaction. I've got methane burning in oxygen. So it's exothermic, so that means our delta H is going to be negative. So if I wanted to draw this, I would make sure that my products are higher than my reactants are higher than my product, because the delta H is negative. I'm going to go down in enthalpy. Neat. And so I can show my reactants here and my product over here. Very simplified reaction enthalpy diagram. Let's look at a more fancy one. Before we do that, let's talk about something. So imagine that I am splitting a coconut, yeah? Well, coconuts just don't spontaneously break open. I think to actually break a coconut in half, not sure about the enthalpy change. I feel like it would release energy. So that would mean my delta H is negative. So I could draw a diagram for this where it's like, hey, I got a coconut, negative delta H, it's going to become 2 coconut halves. But it doesn't really tell us the whole story, because coconuts in the real world don't just spontaneously break in half. In order to break a coconut in half, I'm going to need to add energy to open it. So maybe I'll hold my coconut and I'll smash it on a rock. I have to add energy in that That act of me swinging it and smashing it is adding energy. We can think of that, describe that as activation energy. That's the amount of energy I have to put in to break that coconut in half. So if I wanted to show that, my reaction enthalpy diagram, I would show that as a little hill that I gotta rise over before I can get to my product. So that's my activation energy. Energy that I have to put in to make this reaction go. And this happens a lot in real life. Activation energy is the energy we need to start up a reaction. And some familiar examples would be like splitting a coconut. We talked about that. Or if I wanted to, for instance, start a fire or light a match. I have some matches here. And if I pull out one of these matches, it doesn't just like light on its own. I have to strike it on this box. And that's going to give it a little bit of energy to get that fire going. So that activation energy that I provide by sliding it across the matchbox enables the reaction, this combustion reaction, to get started. So yeah, fires don't start on their own. If I wanted to start a fire in a fireplace or outdoors, I'd need to add some heat before that fire starts. Roller coasters, another example, which kind of mirrors the reaction enthalpy diagrams. If you want to ride a roller coaster, most roller coasters, ting, 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 got to go up a hill before they can launch off. Those cars need to get pulled up the hill, and that requires energy required to activate or start up the whole roller coaster ride. So the activation energy doesn't really relate necessarily to whether a reaction is going to be endothermic or exothermic. Both endothermic and exothermic reactions will have activation energy. And so it's not going to mean if it's exothermic that you'll have a high or low activation energy necessarily. So we can use activation energy to help us determine if a reaction is useful or good. Let's talk about that. Enthalpy in action. This is something that I studied and I think is pretty cool. Water splitting with solar energy. So energy produced by solar energy, if we make it coming in, ideally we need a way to store it because we don't necessarily need to use it all at once. So we need to be able to store energy and so we can use it when we need it later. And water splitting is a pretty cool, promising solution. We can use energy to split water to hydrogen and oxygen, and then later we can react those together to produce water again, get that energy back out. I mean, that sounds really awesome. There's no ugly byproducts to that. It's theoretically super clean energy. But the reaction has a really large activation energy. Because that reaction activation energy is so large, just zapping electricity directly into water to do this reaction isn't really viable. We can see here from this diagram, it doesn't really, our products are, it's a positive delta H, but it's got this massive activation energy here. This is our enthalpy diagram in teal for the water splitting reaction. Now you might be saying, oh, what's up with this purple John? Well, that is to describe something photocatalyzed water splitting. So that is when we use a catalyst. And you can see it has the same starting level of energy and ending level, but it has a lowered activation energy. This is for what we would call uncatalyzed, the uncatalyzed reaction. Now you're probably saying like, what catalysts? What? You didn't mention this in the objectives? No, I didn't. It's a little surprise at the end. Catalysts are cool things that we can use to lower activation energy. And there's a lot of research into making good catalysts that are really good at lowering activation energy. But I want to talk about that more in a later video, so I hope you cannot wait for that, because that's the end of this video. So I hope you feel like you understand a little bit more about what enthalpy is, how enthalpy changes occur during reactions, how we can use enthalpy diagrams to show that, and why activation energy is an important part of everyday life, chemistry, and yeah, it's pretty cool stuff in general. Anyway, that's the end of the video. Ta-ta. Have a great rest of your life.